The mass of a Milky Way is a long-standing question, without clear and precise resolution. An array of estimates exist, many of which seem to partially agree, partially disagree or totally disagree with each other. To address the question of Milky Way mass, the results of Watkins 2019, Eadie 2017-2021, and Karukes 2020 are tested against the cosmological Hubble constant, derived in Episode 10, and the cosmic microwave background radiation temperature, derived in Episode 11. In this episode, when we refer to Milky Way mass, we're referring to its virial mass. Virial mass denotes all the matter within the Milky Way, which is gravitationally bound together. This also includes the dark matter halo. We're also going to show that intermediate Milky Way mass estimates, that is, Watkins 2019, breach particle data group requirements for the satisfaction of the cosmological Hubble constant and cosmic microwave background radiation temperature constraints. However, Eadie 2019 Milky Way virial mass solutions tend to be substantially more compliant. The ideal solutions for virial mass and virial radius, precisely satisfying cosmological Hubble constant and cosmic microwave background radiation temperature constraints, are also presented. In addition, we show that the Eadie 2021 results may be discarded. So, let's begin. The process we're going to execute has already been defined in Episode 11. We recommend viewers to review the preceding episode, if not already done so. If you're already familiar with the process defined in Episode 11, a representation appears on screen. We'll be plugging in various values of Milky Way virial mass, as determined by several authoritative sources, and testing them against the cosmic microwave background radiation temperature. If their values of virial mass fall within the experimental tolerance of the particle data group 2022 cosmic microwave background radiation temperature value, then their virial mass estimate is valid. If it falls outside this tolerance, then their estimates are invalid and may contradict the standard model of cosmology. Let's first look at what the experts are saying. Prior to executing the solution algorithm, we need to obtain authoritative opinion on our primary input variable, that is, the solar distance to the galactic center. But what do the experts say? Well, that depends upon whom you ask. One may be forgiven for expecting harmony amongst authoritative sources, but that isn't necessarily the case. Astrophysicists may take the position that the solar distance to the galactic center is well established and tightly constrained. However, to engineers, it certainly doesn't appear that way. As you can see on screen, the variation of estimates for the solar distance to the galactic center is not trivial. We suspect that the main cause for this is because the astrophysics community lacks a governing authoritative body, such as the particle data group. The lack of a source of truth makes it very difficult for follow-up researchers whom depend upon this information. So, by necessity, we'll utilize the average value. However, the situation with virial mass estimates is worse, experiencing a significantly greater degree of discordance. The spread of these results, as well as estimates from other authoritative sources, implies that the astrophysics community has a fundamental problem which needs to be addressed. In this episode, we offered the proposition that a virial mass value constrained by cosmic microwave background radiation temperature provides a logical and powerful community-wide definition of Milky Way virial mass. Let's now run the numbers. Executing the process defined on slide 2 allows us to test the virial mass estimates provided by Eadie, Karukes, Watkins and Storti against the cosmic microwave background radiation temperature. Utilizing this process, we're able to firstly test the virial mass estimate for its compliance to the cosmological Hubble constant, that is, the power spectrum Hubble constant, and secondly, to test the virial mass estimate for its compliance to the cosmic microwave background radiation temperature. Upon executing these compliance tests, we find that the Karukes estimate passes the Hubble test, but fails the cosmic microwave background radiation test. However, the Watkins estimate fails both tests. Notably, the Storti estimate passes both tests, but the Eadie output produces some interesting results. With the Eadie results, we see that the 2017 virial mass estimate passes the Hubble test, but fails the cosmic microwave background radiation test. In contrast, we see that the Eadie 2019 virial mass estimate passes both tests, and the Eadie 2021 virial mass fails both tests. So what happened, what's changed and what went wrong for Eadie? Well, quite frankly, only Eadie can answer these questions, but it should not escape your attention that the Eadie 2021 virial mass estimate is 74% larger than the Eadie 2017 estimate, and 54% larger than the Eadie 2019 estimate. So why would Eadie, seemingly, flip so dramatically from the correct answer to the incorrect answer? The change in opinion wasn't minor, it was extremely significant. This alone brings into question all of the Eadie results. They were incorrect either in 2017 and 2019, or they're incorrect in 2021. Either way, the publication peer review process has been proven to be substantially lacking. Let's now analyze another widely cited result. A simple algorithm constructed within the MathCAD 8 professional computational environment facilitates the determination of the required solar distance to the galactic center, associated with the Karukes 2022 Milky Way mass estimate. Although Karukes does not explicitly claim his mass estimate to be virial, it is implied and we shall assume that it is. In such a case, we clearly see that the required solar distance to the galactic center is obviously impossible and boldly contradicts widely accepted particle data group 2022 limits. Therefore, the Karukes 2022 Milky Way mass estimate may be discarded. Let's now look at the ideal solution. Utilizing the process defined on slide 2, we're able to identify the ideal virial mass solution for the Milky Way, satisfying the experimentally verified value of cosmic microwave background radiation power spectrum Hubble constant, as well as the experimentally verified value of cosmic microwave background radiation temperature. In other words, we have found the ideal virial mass solution for the Milky Way, constrained by the cosmic microwave background. Moreover, we may also utilize the same set of equations to explain the cosmic distance ladder Hubble constant measurements associated with Cephids. We achieve this by considering encircled mass, not virial mass, and encircling radius, not virial radius. However, these results are not cosmic microwave background radiation temperature constrained, and nor do they need to be. Why not? Because cosmic distance ladder measurements are not, and cannot be, associated with the cosmic microwave background. This is the origin of the Hubble tension. Similarly, we may repeat the process in order to explain the cosmic distance ladder Hubble constant measurements associated with red giants. Once again, this is achieved by considering encircled mass, not virial mass, and encircling radius, not virial radius. As before, these results are not cosmic microwave background radiation temperature constrained, and nor do they need to be, due to the origin of the Hubble tension. It is extremely important to note that we have resolved the Hubble tension, and shown that it doesn't exist. We have proven this by calculating all experimental values of Hubble constant, in all forms, utilizing a single equation. In fact, this is a second instance in which we have resolved the Hubble tension. The first instance was in episode 10. Please review episode 10 if required. Let's now summarize what we have learned. So, what have we learned? We have shown that Karukes 2022, Eadie 2021, Karukes 2020 and Watkins 2019 Milky Way mass estimates may be discarded. Their results are not cosmic microwave background radiation temperature constrained. Therefore, they're in tension with the cosmic microwave background radiation power spectrum Hubble constant. Moreover, we have calculated the ideal virial mass limits for the Milky Way, constrained by cosmic microwave background radiation temperature limits. In addition, we have resolved the Hubble tension, and proven that it does not exist, by demonstrating that the cosmic microwave background radiation power spectrum Hubble constant, and the cosmic distance ladder Hubble constant, may be determined utilizing a single equation. Very importantly, we have shown that cosmic distance ladder measurements of the Hubble constant need to consider the mass of the host galaxy, and the distance of the celestial object being studied, to its galactic center. For viewers wishing to consult literature relevant to this episode, you may do so by accessing the links shown.